Everyone, and welcome to the May webinar presented by the Underground Construction Association Young Members Group. I have a handful of announcements today before we begin the webinar. My name is Erin Clark, and I'm one of the members of the UCA of SME Standing Committee for the UCA Young Members Group. I am the outgoing Professional Development Chair, and I'm joined by Anthony Bauer, the Chair, Shannon Goff, the University Outreach Chair, and our newest committee members are Everett Litton, the Membership Chair, Demetrio Criscolo, as the Media Chair, and Colin Sessions, the incoming Professional Development Chair. First, I'd like to tell you about last month's World Tunneling Congress. It was hosted in San Francisco, and for the Young Members Group, it was a great success. For those that don't know, the Young Members Group sponsored a student scholarship, and that gave the students admission to the conference and $1,000 to travel to the conference. This enabled 40 students to actually make the conference, and the executive committee was so impressed with our success. We had 120 applicants of the 40 that attended the conference, that we have been approved for the same amount of funds. So students, prepare yourself that you can apply for the ROTC and get some money to help get you to conference next year. ROTC next year will be in San Diego, for your information. And then also, what else went on during conference was the UCA and the ITA Young Members Groups had a networking event. This networking event was attended by 165 people, and it was a great opportunity for people just to really get familiar with everyone else in the industry that is our age. So next month you can join us in June for a webinar on the Victoria Street Station. It will be presented by Dr. Beatty of Beatty Consulting. The Victoria Street Upgrade Project is in London, England, and you can register for next month's webinar on our events page. Registration for this will open by the end of the week. And I just want everyone to keep in mind that we're limited to 100 registrars, and we've never hit this number until today. So it's wonderful that we're reaching so many people, but just keep in mind that if you are watching the webinar with a group of people, or if you know people in your company are watching it, just step into a conference room and watch it together so that more people can join us, because we have 100 registered, but right now we only have 44 attending. So we're trying to reach more people and make it more accessible for everyone. And on to today's. So today's webinar is going to be on it'll be on microtunneling in hard rock and mixed face conditions. Lester Bradshaw is presenting to us. Mr. Bradshaw has begun his career at the age of 14 working in a tunneling family, and his father owned the tunneling construction company. In 1982, he completed his bachelor's and master's in civil engineering for Georgia Tech, and he went on to get his MBA from Harvard University. He then came back to his family company, and he worked as vice president and corporate secretary, and he also played an active role in the business by being a tunnel supervisor, a chief engineer and estimator, and a safety officer, financial manager, and in 1991, he became the president and treasurer. Under Mr. Bradshaw's guidance, Bradshaw Construction has successfully completed over 1,000 tunnel projects in the United States and Puerto Rico, totaling 250,000 linear feet and construction value over $5 million. Bradshaw Construction is known for employing cutting-edge technology and industry first, including 1,200 linear feet of a 192-inch tunnel built under the compressed air using NATM. In 1991, they successfully completed the first microtunneling project in the Mid-Atlantic, and in 2004, they installed the first hard rock crystalline rock microtunnel. In addition, Mr. Bradshaw has been the managing partner of several joint ventures, building tunnels up to 14,300 feet in length and shafts up to 150 feet deep. Mr. Bradshaw also plays an active role in the industry and is a 39-year member of the ASCE and currently serves on the board of directors for the North American Microtunneling Association. Representing the NAMA, he is instrumental in publishing the 2015 ASCE Standard Design and Construction Guide lines for Microtunneling. He's a second-term member of the Executive Committee for the Underground Construction Association of SME, and he serves on the board of the nonprofit chair for NSRC for the last 8 years. And Mr. Bradshaw, lastly, is a member of the MOLD organization. Lester, when you're ready, if you could share your screen.
Thank you very much, Erin, for the nice introduction, and good afternoon, everyone. Well, it's afternoon for the East Coasters like myself. I don't know about the rest of you attending. I was asked to do this seminar just a few weeks ago, webinar, and I wanted to talk about microtunneling in rock. It's something that's not done all that often. If those of you who are not familiar with microtunneling is pipe jacking. It's just using remote-controlled equipment, much like ROVs that are searching under the water for things like the Titanic. We can control these machines remotely from the surface, and they are very sophisticated with slurry systems for holding face stability and transporting the soils, and very efficient. Today I want to tell you a little bit of facts, things we've learned from a contractor's perspective on microtunneling in rock, whether it be sedimentary or igneous or metamorphic rock. And then a quick, not so quick, but a case study of an actual job where you have to get a sense of what it's like to be a contractor. I wrote this paper several years ago, and it's available on my website at www.bradshawcc.com. That's www.bradshawcc.com if you want to get the greater details. We wrote it from the perspective, like I said, the family business has been around since for 53 years, and we've been doing hard rock TBM tunneling for 20, microtunneling for 25, and 12 years if actually hard rock microtunneling. Before the 25 years, we were hand miners, up close and personal with the rock, right in the face, drilling, blasting, or spading, shoveling, of which I served about a 10-year apprenticeship right there to start with. Many in the industry, and bluntly among the engineering community, even to this date, and this has been several years since I gave the paper, are unfamiliar with the ability of microtunneling to be able to cut rock. There has been, however, significant developments in that industry over the last 20 years. When it was first attempted, I'm speaking this time in rock, when it was first attempted, it was very little success, primarily because the contractors that were many of the original microtunneling firms were not tunneling firms. They hadn't hand mined or used TBMs before and didn't understand the limitations. Also, there was one major development in the industry by Heron Connect, which was face access, the ability to go through the machine and change the cutting tools as they wear out when you're cutting rock. That was a critical aspect. And at point, when they became available is when Bradshaw decided that it was time to try to cut hard rock, and we purchased the equipment in 2004 and did 6,000 feet of 60-inch OD concrete polycrete pipe in Baltimore City in mixed face, mixed reach, and solid rock. That so happened to go all the way up to 43 PSI. Prior to 2004 or so, there had been quite a bit of sedimentary rock microtunneling. It's soft. It behaves like dense soil, a significant amount of it in the Midwest of the United States. And in fact, some records were set, I believe, in production with pipe jacking through soft shales, clay stones, etc. And we've done several of those projects, and it's quite a bit different when you can push 50 to 120 feet of steel casing through the ground in soft rock, as opposed to sometimes in crystalline rock spending 12 hours to cut 8 to 12 feet. What do we mean by hard rock? It's igneous and metamorphic rock formations. They're crystalline in nature, they're abrasive, and in worst case, they're also massive with very little fractures to them. Often many people tend to look at just the unconfined compressive strength, think that tells you a lot, but that's highly fractured rock can be very high ECS, 30, 40,000, but if it's got a lot of fractures in it, then the disc cutter technique of mining is quite effective, as opposed to we've seen massive rock as limited as 12, 15,000 psi, even 10,000 psi UCS to be exceptionally difficult to cut through. Early attempts, as I mentioned, were made in the 90s, and they were extremely limited in their success. Most of them completely failed. And we're talking distances of going 15 to 20 feet and having to extract, backpull the machine to even attempt to try again. The cutters wore too fast. You couldn't change them except by pulling the machine out or digging a rescue shaft. As I mentioned before, face access was introduced, however, only down to 59.25 inch TBMs. The primary reason for that is in a 59.25 inch OD TBM, there's only an 18-inch port, looks like a porthole, or it looks like a torpedo tube door right up through the center of the machine to the back of the, and the cutting chamber itself is relatively small. It's you truly have to micro individual there that hole and change the, but we do it. The new HK series TBMs that came out back then were considerably heavier, had a lot more torque to cut rock with. We studied closely all the early projects as we could and compared them to our main beam TBM machines, of which we have used one at 83 inch and a little bit larger. The other thing to keep in mind always is if you get below 59.5 inch, you don't have face access, and therefore the length of a microtunnel is highly dependent on how long the cutting tools will last at the face, particularly the perimeter gauge cutters. If you might be able to go 200 feet, you may be able to go 500 feet in a soft shale, but in a hard crystalline rock, you may not get 25 to 50 feet before you're going to run out of gauge. This is a typical rock cutting head. This one happens to be built by Heron Connect. This is a 60-inch rock cutting head. It's the first one we used, and they're quite effective. These cutters can be loaded from the front of the machine, which makes it easy for servicing when they're above ground. You load them from the back when you're below ground. And through the cutting wheel, and you can see that porthole in there, and that's what you crawl through to make the cutter change. From inside the machine, when they're in the shop, they're nice and clean, you can see that door up there, and that door is much like a torpedo tube door. You don't bolt it, you disconnect it from the slurry line, or in this case, a bit line, and crawl through. And after you've done a drive or partially through the drive, this is what it looks like after a while of crawling through, because in the back of that cutting wheel are cuttings and slurry sometimes. You have to be able to pump them out and crawl up in there. And in this instance, you're looking at triple kerf cutters. I think this happens to be a mixed ground cutting wheel we were using. Fundamentals of physics when it comes to rock cutting. Large, up to 72 inches, the maximum diameter cutter you're going to get is 11 inches. That's to be the red double kerf cutter on your left in this picture. We recently purchased a Robbins double shielded machine where you can front load the cutters, and we've got them up to 14 inches in diameter. On your typical TBM, I believe at Robbins, they have one that's 88 inches, but typically from 96 inches and above, they will front load 17-inch cutters. The issue is the difference between back load and front load is the front loaders have much more bearing surface on the front of the machine, whereas the back loaders, you have to cut out the actual cutting wheel to fit the disc cutter up in, and trying to get optimal spacing, which is about 75 millimeters, between kerfs and fit enough of them on the face, across the face, that they don't get in each other's way and allow room for ports for the material, the cuttings, to come through the head. Becomes a very complicated and difficult problem to do the smaller you get. The other key to this is look at the thrust capacity. An 11-inch cutter is 17,500 disc cutter capacity. And that only comes if you create what's called a monoblock cutter. The cutter on the left there is around the outside of a bearing race, whereas the other two are what are called ring and hub. Ring, a cutter that is put onto the hub. That cutting ring is replaceable, whereas the hub can keep going, the bearings can keep going. So the microtunneling cutter, they do this in order to get the maximum size bearing in. When you look at a color, there's two things you're worried about or concerned with. One is the amount of metal that's there to wear away due to abrasion and whatnot. And the other part is how big is the bearing you can put in there. And that controls the amount of allowable thrust that you should put onto it. And those are your limitations at 11, 17, 17.5. That 17-inch on the right, 70,000 pounds of sustained load. The 14 is in the 35,000 pound. Oh, one is a giant size hammer and the other one's an itty bitty hammer. It's a micro hammer. And when it comes to cutting rock, the bigger the hammer, the bigger the chips, the faster you go. Microtunneling, though, why do it? And, why not just have an all rock tunnel and use a conventional main beam machine? Well, there's a tunneling. We do a lot of water and sewer work, particularly shallow gravity sewer work. And what you see there is you don't see solid rock. You see mixed face, mixed reach. You see highly weathered to competent rock. Main beam tunnel bores do not do in the shielded, double shielded Robbins machines do not do well in mixed face, mixed reach conditions. We just finished 3,000 feet and multiple drives in Baltimore City. And every time we hit highly decomposed rock, the machine clogged up and we got terrible production. In those areas, the microtunneling machine would have gone quite well. The reason we used the Robbins was because we could put 14-inch cutters on the front, and the bulk of the job was solid, hard rock up in the 30,000 range. The smaller the diameter, many of you are engineers, the smaller the diameter, the stronger the rock is, because we have a lower radius on our arch, and you have less flake drop out of the matrix jobs where our 60-inch rock machine will go through and there will be no blocky fallouts of the crown. Same job where we attempted to use our 83-inch main beam Jarva machine, and the blocks just slid right out of the shoulders. The dip on the rock was in the 70 to 80 degree range. Came in, damaged the cutting wheel, and prevented us forward operation. So the smaller can be better. And third or fourth here, and we do a lot of this, the microtunneling machines are watertight, waterproof. You can drive them right out into the bottom of a river, bottom of a lake. In fact, our first two hard rock microtunneling jobs, the first one was a double raw water intake in the Susquehanna River in Pennsylvania, and we recovered the machine twice underwater with divers. The key to rock microtunneling, understand the geology, and then understand the limitations of the equipment, the pipe jacking materials, and then the meters themselves. We want to know what the type of rock by drive. Many times, like, for example, the recent Baltimore City job, there were 5 drives that had to be, and each one was different. We want to know where the rock is within the drive. Therefore, testing of the rock to find the zones and the ridges and whether there's any peaks and valleys or is it solid. At least here on the East, tremendously. More in the Midwest, the material is sedimentary and it's laying relatively flat. But you're going to get areas we looked at in Denver. The rock was up on a 40 to 50 degree, and therefore you were mining through multiple layers, multiple zones, and knowing where those zones are can be critical. We were not the low bidder, but it's going to be quite challenging to any conventional TBM because you go from 500 PSI shale to 25,000 PSI sandstone, and those behave incredibly different on the rock cutting wheel. The other area that we look closely at is the orientation and spacing of any rock fractures. We can find, and particularly we want to know, all you engineers out there, we want to know whether when you test it, it's a structural or non-structural failure. You'd be surprised how many testing labs don't note that fact. And if it's a structural failure, the UCSs are almost worthless. Search our abrasivity. Very important with microtunneling because our cutting tools are so small that they wear away quickly. The RQD is for decades and prior to microtunneling or any type of to get a sense of how the rock may break. In days past, a low RQD rock was maybe a little because your gases from your explosion, your powder dynamiting might escape these. In microtunneling or any rock tunneling, the lower the RQD, the better, unless the roof falls in on you. But it cuts much easier. We also look at things from point load tests, punch penetration. We have had, sadly, you learn from experience, thin section petrographic analysis can be critical because we have run across several situations here on the East Coast with a condition called rock suturing, mineral suturing, where the grains of the rock, when you look at it under a microscope, they're particularly long and they are chemically bonded together rather tightly. What does that do? What's the behavior issues? The behavior of the rock then becomes much less brittle, that fractures quickly and easily with a disc cutter pressuring it. It becomes more ductile and tends to bend rather than break. The result is disc cutters tend to sink, they wear faster, and you make a lot of powder. And when you're making powder, that means the energy it takes to cut is much higher because you're turning the rock into smaller pieces. And we've tried to do as much historical research when we look at these tunnels to see if there's any areas in there. Our particular experience has been with amphibolite or diabase, and those two particular types of rock are exceptionally ductile in their behavior, and it can be incredibly hard. A couple recent projects. We did a project in between Baltimore and Washington, D.C., where the amphibolite peaked out at 55,000 psi UCS with surcharge in the 4s, and we chose to drill and blast that job. Given the size of the diameter of the tunnel, there was no way that we thought we would ever cut it with small cutters. Diabase can be just as bad or worse. We've seen that in certain situations, and it is equally or even greater ductility, hardness, greater abrasivity, and very difficult to cut. So when we find conditions like that, we either avoid them or we look for alternative means and methods, drill and blast or much larger TBMs. Now you can model the performance of a TBM. We just did it for a project that we're bidding today, in fact, where we had Colorado School of Mines or experts such as Levette Osdemer and others out there take our information off our TBM, take the rock information from the soil studies, and give us a prediction of instantaneous penetration rate of the machine through the rock itself. From there, we have to determine how much our uptime is, how much availability of the machine, how hard we're willing to push it, what kind of RPM the machine we choose to have. We have multiple settings on it, etc. To determine the advance rate, because when it gets down to bidding the job, it gets down to how many feet of tunnel a day. And I just mentioned that when we look at things that are, one thing to keep in mind, I'll give you a quick example. A Robbins TBM 72-inch, even though it's a double shield, it does several things that our machine can't. For example, it carries cutters at 40, more than almost 2.5 times the thrust capacity. So we can push on the rock much, much harder. And therefore, its penetration rate is more than double what a microtunneling machine is. As important or more important is the microtunneling TBMs they only, at least they turn at 2.5 to 5 RPM. Whereas the Robbins TBM turns at between 14 and 15, or up to 15 RPM. We figure more like 10 to 11 under load. But you can see that just by the simple formula that you take your instantaneous penetration rate times the number of RPMs times the number of hours in a shift times the percentage of the time that the machine is turning, the cutting wheel is turning, to come up with your day's production. But it's a scalar multiple of RPM. And so there alone, a conventional TBM is 2 to 3 times more productive. For timber cutters, I think I mentioned it. These are the cutters out at the perimeter of the cutting wheel. They're almost perpendicular, the ones far out, to the direction of the mining. And they are highly sensitive to the abrasive rock. They also cut the hole that allows the TBM to go through. And as they go through the ground, they get smaller and smaller, which means you're basically cutting a series of wedge holes and driving your machine in. And if you don't pay attention and that gets down, you can wedge your machine. And once you stick one, it's very difficult then to push the rest of the machine through there. Overcut. It's a big deal in the microtunneling industry in soft ground that the overcut is always concerned to be too great, it would lead to settlement over the pipeline. In rock, that's not an issue. However, many times we look at specifications that still require way too small an overcut in rock because they're thinking that it's a spec from a soft ground job. The fact is that your overcut for rock needs to be 25 to 50% greater than soft ground to allow the wear of the gauge cutters, that little triangle gauge cutter, because every time you replace it, you now cut a bigger tunnel. You literally have to go in there to replace that one, and sometimes jackhammer a hole out to put it in so that your machine can get bigger again. We think that the contractor should determine this factor, and I know this is a bit into the weeds for some of you, but if you're on the engineering side, just keep that in mind. There's times the contractor should determine things. We can't make the overcut too large, or we wouldn't be able to steer our machine. We've run across a couple of really nasty problems with microtunneling, and we call it cam locking and pipe wedging. You do get flaky sometimes. You get chunks that break off, and when they do, they wedge around the machine, and they can wedge around the pipe, and you get significant spike loading. If you're pushing the entire pipe string from the shaft, let's say you're out there 200 feet mining, you have to overcome any friction along, say, steel casing pipe and the TBM itself. I mean, typically a TBM can be anywhere from 12 to 40 feet long, depending on the various segments that you put behind it. All of that adds up to areas where you can get friction loading, and cam loading creates a spike load. We've seen it where you're jacking along at 100 tons, and almost instantaneously it jumps to 200, 250 tons. And then that rock that gets in the overcut area breaks down or gets pushed out into softer areas or just crushes, then the pressure will drop again. What that leads to the problem of is surge loading of the cutting wheel, because every time that rock lets go, then the whole pipe string goes forward and jams the cutters into the face and creates shock loading, and we've seen damage from that. So we recommend you put what's called a telescopic tail can behind the machine, directly behind the machine, and advance that forward with that can and not with the jacks from the shaft pushing the whole pipe string. Finally, it depends on the material. Some people have tried to use materials that are inappropriate for rock, such as clay pipe. You want a pipe jacking material that's got significant tensile strength. All rock machines do not cut. When they cut the material, they cut a perimeter hole. But the pickup buckets, that's what the scrapers are around the machine that pick up and try to force it into the front to be transported, are always a quarter to a half inch smaller than the overcut. Therefore, you're always leaving material in the bottom of the tunnel. And as that material, as you push forward the machine, that material can pile up. And in some instances, if the pipe being pushed is irregular, meaning it's not round and therefore it's sitting off center, it can literally scrape those cuttings up, pile them up, and the entire pipe string get wedged against the roof of the tunnel and break the carrier pipe, and or freeze it in place from jacking pressures. So proper choice of the carrier pipe is critical for pipe jacking in rock when you think about it on the tensile strength point of view. So today, I mean, rock microtunneling is absolutely a fact. We do it all in sedimentary rock, but now it is in crystalline rock. Face access is the real key that saves that. There's not a drive we have today that we don't go out into the face of machine cutters. And the real key to it all is to know where, when, and how to use microtunneling in these types of conditions. Now, I want to give you a little example of what it's really like to do this for a living. We did a project in Reading, Pennsylvania, and this is a site view of the shaft in the banks of the Schuylkill River, just on the south side of Reading, Pennsylvania. I'll give you the typical presentation. This presentation as well is on our website. If you'd like to read, there's a paper that I wrote about it that gives you even greater detail than I'm possibly going to be able to cover today. It was a 42-inch force main project and for the city of Reading. We worked as a subcontractor to a local contractor, Pack Construction. Pack was building 7,000 feet of 42-inch DIP force main. It paralleled an existing steel force main that was on the verge or had some problems with failing. It crossed and paralleled the Schuylkill River, and it's located on the south side of the city. And here's a good picture of what you are seeing. The microtunnel is up at the river crossing on the north end of the project. The rest of it ran right down the river bottom, along the edge of the river all the way, paralleling the existing force main. It was a project to create redundancy, to allow maintenance. They couldn't shut down the existing force main to maintain the steel, to reline it or repair it. Without that line, the city was a desperate problem for sewage treatment. They would be able to split the flows in the future and create less wear and tear on both lines. And they needed future capacity. So this is what the purpose of, that's what the owner's goals were here. But it required crossing the Schuylkill River from the pump station. Pump station had contaminated groundwater. We had to work alongside that deteriorating existing steel force main. We had to work in a flood zone. The receiving shaft flooded regularly, and the mining shaft or launch shaft was subject to flooding as well. We had extremely restricted access because we weren't allowed to interrupt that pump station's operations. And we had partial rock at both shafts, which can make it difficult to install when you have sedimentary material over rock. And so we basically had mixed reached shafts. Not only you'll see that it was mixed reach tunneling, it's mixed reach shaft. And what we mean by that is soft ground over rock. And that requires different types of mining techniques, or you may only use one mining technique, but it can be severely impacted because you're trying to overcome the worst condition, and sometimes that doesn't make it easy to do either conditions, but it does get the job done, and that's what you look for as a solution as a contractor here. Microtunneling, I'll give credit to the owner and the engineer. They knew what they didn't know, so they pre-qualified microtunneling contractors and tried to learn about what it is that they were looking for. And further, they required that the general contractor, none of which were microtunnelers, would write in who was going to be their sub. They did not want bid shopping. They did not want any questions after the fact, having gone through the pre-qualification process. It was an independent pre-qualification well in advance of the bid itself. Soil borings. This is interesting, by the way. I've never seen this many soil borings taking on a microtunneling in my entire years of doing this work. There were 12 bores in 400 feet and 9 in the river banks itself. Often when we do a river crossing, for permit reasons or other reasons, we may not even get a bore in the river. There, we felt extremely confident that what we thought we knew, the rock of the river. It was highly weathered to strong. The jacking pit was highly weathered, decomposed, and frankly, below the tunnel when we started out. We were supposed to start out in alluvial material. However, on the receiving shaft side, not 30 feet from the existing force main, it was hard rock, up to 34,300 psi UCS dolomite, and it was massive in nature, 100%. The surcharge was relatively low. We didn't expect wear on our cutters on the perimeter gauge. Anything below about 3.5, I don't get too concerned about. Depending on the distance of the drive, at 430 or 60 feet here, it was quite doable and not the real risk. The risk here was the mixed face, mixed reach, and the massive nature of the dolomite. We expected a jacking shaft, just like say alluvial soils all the way down with rock below invert. The tunnel itself, we expected 220 feet of alluvial soils, 40 feet of mixed face transition rock, and 176 feet of hard rock. That's 436 feet, not 460. That's based on the geologic report, which was extensive. Here's just a plan view. We tunneled from the west side actually from the north side. This is turned a little, to the south side of the Schuylkill River from the plant which is up on your upper left. And here is the anticipated rock profile. We felt that there's more than enough information that you could quite clearly define this. We were going to go from a sea-compiled jacking pit on the left to a drilled receiving shaft on the right. And you can see where the rock profile, we plugged it in, and we had 12 bores to determine where this was at. Along the river banks, you can see what the typical rock outcrop looked like. Most of the rock laid in these layers to it, and interesting enough, it had quite significant, just reasonable, and on the surface quite interesting, and probably cut relatively well. However, at the receiving shaft, this is not what we had. The rock there was massive, so it was a little different. I will go into a little bit of the weeds of the contract. They made the contractor responsible for selecting the type of TBM and the cutting wheel. In this instance, we of course had to choose a hard rock disc cutting cutter wheel because we had to, and within the alignment, we had to go through up to 34,000 psi rock. We didn't have a choice. That is not the cutting wheel you want on alluvial soils. The openings in the cutting wheel are relatively small. The material comes in slowly. It impacts production, and it's not really appropriate. But we didn't have any choice. We could not put a shaft in the middle of the river and then only mine the hard rock one way and the soft ground the other. We were responsible for retrieving the MTBM if it was stuck or fails to finish the tunnel. Now, that would have been exceptionally difficult in this river. Again, we had to choose a method that almost guaranteed that no matter what happened, we could get through the soils. We had to be able to progress past or through any objects, any obstructions, which is a little curious because the next statement was we were only responsible for mining obstructions up to 1/3 of the ID of the pipe and up to 30,000 psi. We knew that the rock was up to 34.3, so there were some inconsistencies in the specification. They specified that our line and grade, although this was a force main, they specified line and grade to be plus or minus 2 inches of the casing. And this was a 2-pass tunnel. We were jacking a 60-inch steel casing, and then we would thread, I believe, a 42-inch ductile iron pipe inside of that. Well, the relevance on the tolerance is where do you want your pipe? As long as you get through the casing without touching, typically a ductile iron pipe, anywhere along the line, it should have been acceptable. But we could live with this plus or minus 2 inches, and I'll give you a reason why later. The shield overcut, though, was limited to less than 1 inch. And yet the spec said then the annular space, the distance between the OD pipe to the ground, could only be a 1/2 inch. So this made absolutely no sense to us, nor was it relevant to what is a good standard practice for overcut within rock. So luckily the owner did not, or the engineer did not take exception to our submittals along these lines where we used more like close to a 2-inch on diameter. Inconsistencies, I just mentioned it. The rock was actually harder than they told us what the limits were. The tolerances were for the casing, not the carrier pipe. The annular space was less than the shield pipe overcut, etc. And in rock, I'll repeat myself, we have to have overcut to steer the TBM. That's number one. We have to be able to also, in rock, to account for cutter tool wear, particularly on gauge cutter. Even though this was a low surcharge project, you still have to be worried that gauge cutter will wear. And as a result, you don't want to, you could wedge the machine. So you're going to shim your gauge out. You're going to take a larger bite. Worry about the extra around the machine. Rock cuttings wheel, I mentioned that they can pick the carrier pipe up and push it against the roof. In this instance, we weren't particularly worried about it because at 460 feet, we thought we would have good luck at being able to overcome any additional resistance that developed as a result of that. There were other requirements, like at the jacking shaft. We were highly limited in our plant, to affecting the plant operations. We had to coordinate with the plant to get in and out, and we developed a good working relationship. They were supportive because they know that they needed the extra line. So although the specifications were rather extensive on this, in fact, the working relationships were quite good. We had to work in contaminated ground, which means they also limited the infiltration to that jacking shaft to only 50 gallons per minute. And when you're right against the river, that's a significant challenge. Weathered rock was within 5 feet of the invert. So how do you seal your shaft off so that you can, whether you excavate it, we intended to excavate it subaqueously and then pour a trimming slab in the bottom to seal off the water. But we chose, it wasn't going to work. We knew we couldn't, hard rock, so we chose secant piles. Here's a picture of the secant pile operation. Many of you have seen this. It's a drill rig, custom drill rig that comes out, drills each pile, cases them, pours your concrete in them, and pulls the sleeves out, and then they do every other one. I can drill the center of them out. Actual conditions, though. When our driller got out there, our secant pile contractor, he hit weathered rock 12 feet higher than shown on the plans. It more than doubled the time it took to drill the secant piles out and made subaqueous excavation impossible. In fact, you'll see here, this is what the bottom 10, 12 feet looked like. We had hoe ram down. We were not allowed to blast and never anticipated blasting with it. But we did get it down eventually, and we put in a reinforced slab to control any possible water pressure from seeping through the rock itself. The receiving shaft, again, was no blast due to the existing force main. It was just soft alluvial soil, river deposits over top of massive dolomite. There was exceptionally limited access to get to it, and it was about 6 feet lower than the launch shaft, and therefore much more subject to flooding. What we chose to do was to drill that shaft in place, relatively small. In actual fact, when we got over there, that for the bore log was exactly right. It was perfectly for what it said it was. We were no surprises. Our contractor found, however, that the massive dolomite was a little tougher than they thought to drill. They took a little extra long, but they drilled a nice 9-foot ID shaft. Now, a 9-foot ID shaft to receive a 60-inch OD machine is very... We've done it before, and we've done it several times. In this instance, it worked because the length of the tunnel was not particularly long, and we could get that machine. We have a particular MTBM built for coming apart in segments into a small diameter shaft. It does mean, though, line and grade control has to be exceptionally close. We've only got about a plus or minus inches of tolerance. Off any more than that, it becomes dang near impossible to get the machine out of a 9-foot ID shaft. This is a picture of what the rock drilling looked like, and you can see the rock down in there. It tends to be massive. There were some chunks that came out of it. We used a modified, as I mentioned, the TBM. We used a modified one that can be taken apart in segments. It takes about an extra shift or more to take it apart as you recover the machine, but well worth it when you can drill a small shaft rather than hoe ram a much larger one. Drive tolerances are tighter than normal. We had other issues there where the tunnel had been raised. The original geotech report had 10 feet of cover to the bottom of the river, but somewhere along the line, the owner or the engineer decided to raise the tunnel, minimize shaft costs, I suppose. But we only had one diameter of cover shown at the bottom of the river. I mentioned before, this was mixed face, mixed reach. What I mean by mixed faces, you've got alluvial soil, say, over rock, right, and the heading of the machine. Mixed reach is so much of one type material, so much of another. We used a full disc cutter wheel, as I said, because we had to cut the rock, so we had to use that in the soft ground. It did allow us face access to change the cutting tools. We did have to deal with the inefficiency of oils, and we increased the annulus space to mine the rock. This is the type cutting wheel we used. Here's a picture of us actually mining. You can see the exit wall with the exit seal, a double gasketed exit seal because of the river's proximity. We are jacking a Permalock steel casing. It comes in 20-foot joints. This is a indexing frame. It moves forward in about 1 meter strokes, and then it re-indexes and moves forward again and chases itself across the shaft. Very efficient and it's the shortest type frame you can use, which minimizes the length of the shaft necessary. What did we find? I mentioned before, the rock was high up in the mining shaft, or launch shaft. We also found the rock different under the river. We found, I think the key is, we had 112 feet of highly weathered rock, which we found was mixed face, and mixed face rock tends to throw the TBM offline and grade easily. We have to mine slower when that happens to try to cut and turn into the hard rock portions and hold the machine in place to cut a spot through that hard rock. It can be done, but it's very... Then we had 84 feet of alluvial, surprisingly had what we call stones in them. And that can, like boulders, core stones, they can jam the head. And we hit in the middle just pure river gravel, which can sometimes pour into a TBM cutter wheel and lock it up. We experienced a minor amount of that, but it was concerning because if the head locks up like that, there's hardly any way to do, you can't enter the head because of the water at this head. At that size, going to compressed air, we couldn't have held the compressed air under the river, so it was a very dicey situation when it happened. Then we hit almost 44 feet of more rock than we anticipated. So here's the real profile we believe that existed out there. And you can see on the left side how much more rock, mixed ground than we had. I mentioned the river gravel clogged the slurry system, the shallow cover returned to the bottom of the river. Then that gravel poured in our bentonite, both the bentonite in our slurry and the bentonite lubrication that we were pumping outside the casing pipe could escape to the river. Our advance rates were lower than anticipated. They were in the 10 to 14 foot per shift range. Face intervention was required and in the solid rock. And we had to do some special annulus grouting to even access the face to prevent the river from coming into us along the annulus of the casing. We had a disc cutter bearing failure. This is not a gauge cutter. This is a face cutter. We've seen in microtunneling now that because of the small openings in the cutting wheel, it's our belief that the cuttings tend to pile up in front of the machine and create what's called regrind, where you're regrinding the material and it packs it in around the bearings, around the cutters themselves, and it tends to penetrate the bearing housing, and eventually the bearings lock up. When they lock up, then the head just skids the disc cutter along and it flat spots it. We found this one before, I believe, the cutting wheel locked up. If that wears away far enough and you get the actual face of the machine itself against the rock, the face of the cutting wheel against the rock, the head will typically lock up at that point. But we were able to get through. We made it about 400 feet before we had to change cutters. Get out there to cutter, we had to grout around the machine because the flow rate of the water coming through the head, it was too great. So we grouted around the machine. We were able to go out and change the cutter. Then we were able to advance the last 30, 40 feet into the side of the shaft. We grouted again at that point to cut off the water and recovered the machine in segments. So what did we learn? In holes every 40 feet, you still don't necessarily find the top of solid rock in areas where there's a lot of decomposed and weathered rock. We see this from Pennsylvania. We've it all down Carolinas. It's a predominant factor here that finding top of rock is just not very easy, and therefore knowing even with extensive bore log is hard to do. It was our first secant pile shaft, and it was an excellent microtunneling launch shaft. It creates its own nice stabilized exit eye, or entrance eye, we call it, excuse me. And it's great for thrusting against. It's solid. It's watertight. Not waterproof, but watertight. We also know that drill shafts are quite effective. This is about the fourth or fifth time we've done this in areas where access was limited, where the conditions are easier to drill in a subaqueous shaft, trimming a plug in the bottom of it, pump it out. It just means that your accuracy on your TBM must be much greater than normal. If you do make a profit, because you wouldn't be able to recover the machine, and you have to customize your equipment. Mixed face, mixed reach is challenging regardless of how much experience your operator especially has, as well as the contractor themselves. It typically means you're going to go a lot slower, and you're going to have more problems with settlement, with inadvertent returns of surface, because when you hit hard material with the machine and soft, fast raveling or flowing ground above or it will tend to come in. Now, we use bentonites in our slurry in an attempt to cake. Best laid plans. Many times this can happen rapidly, and you're play catch up. and you got to do the best you can. But when these conditions exist, it's best at least discussing with the local contractors, see what their experiences are and what they can do about it, and recommend when you're writing your spec. You can achieve significant accuracy. That machine came out dead on line to within a quarter of an inch, even after 430 feet, after an intervention, and after 3 major transitions in soil type. Bentonite slurry is not very effective. I mean, it's called for in many areas, and many people believe in it throughout the country, but it's not always effective. And we've tried it in a number of situations with mixed results. I do believe that you have to try it. I do believe that sometimes it's an ideal thing, but in other cases, in true mixed face with rock, it has not proved to be a great help. Drive length in rock is limited due to disc cutter wear. We did not change a disc cutter, a perimeter disc cutter. In dolomite, limestone, shale, the wear is not very great. And we see perimeter gauge problems, but what we do see is loss of face cutters due to bearings being penetrated by the cuttings due to the regrind of the face itself. It just seems to be part and parcel of the problem. This also happens on conventional TBMs as well, but not quite as badly. And bluntly, Bradshaw Construction will not bid a rock tunnel that we don't have face access to. We're currently doing a $21 million project for the city of Raleigh through mixed face, mixed reach. And in every instance, we've been into the cutter wheel. A typical 400-foot heading, we're going to be into that cutting wheel at least 2 to 5 times during that drive to change cutters. Public relations. We had an excellent relation with the local newspaper, the Reading Eagle, and I like pushing this up there because I think the guy did an outstanding job of Mr. Schaefer did this for the public to explain the cost of this work and how it actually worked. So we had him out and allowed him to look up into the tunnel and then be into the control container and see the whole operation. A little career, if I was told to mention maybe what I've learned in 40-some years. If you're going to be a tunnel contractor, you really have to study your geotechnical engineering and geology, believing that you know what's below the ground, and then selecting the right equipment, and finally being able to do a good estimate of what that equipment can do. This all comes back to how well you understand the geology. If you want to be the boss, get an MBA. Don't kid yourself. Between the legal and the business requirements in today's environment, you need all the education you can get if you want to run the show. Finally, as far as tunnelers, you're going to learn this out in the field by doing. You're not going to learn this in a class anywhere. Out there and work crews. We've had some engineers who go, well, why do I have to put on hard hat and boots and get dirty? And I said, well, because that's the way you're going to learn, because you can't find it out any other way. I do want to mention that we've been hiring a number of what we think are really appropriately experienced mining engineers. A lot of these are people straight out of school or only out who have spent time mines. They're not afraid to go underground. They're not afraid to get dirty. And therefore, they know how to go out and learn the business. One thing about our business, though, and we don't want to kid anybody about it, and most contractors will tell you there can be quite a bit of travel involved. You got to learn where the job is, and our jobs are relatively short. They vary from 1 month long to 2 years long, typically, and with a whole lot more that are 1 to 6 months than there are 2 years. So there's a lot of moving around, a lot of hotel staying. If you want to see the country, that's a good way to do it. We cover from Florida to Maine to Colorado to Texas, and that kind of travel requirement greatly the industry on the size of the company, the type of jobs they go after, and the position you're in. The higher up you get, the more you tend to get centralized. We're a small operation. We run about 75 people. And we have an office staff, an engineering staff of about 8 to 10, and they work out of the main office, and project managers are rarely on the job site full-time. Project engineers tend to be on the job site because they're learning. So if you're coming into the industry, you start out as a field engineer, you work yourself up to project engineer and project manager. And it so happens that it works out rather well because if you follow a normal family life, you're probably going to get married and you may have kids and you need to be closer to home, at least part of the time, and not traveling so much. We've been able to do that and cover 2/3 of the United States, and our staff is generally satisfied with that type of situation. Lastly, is contracting turning to the dark side? That's what I like to say. It's not I consider it a business. It's not a quote recognized profession like engineering. You don't have a license, although I have multiple contracting licenses. It's not the same as sitting for a PE degree, and it is a different type of business. I mean, we get paid by the foot. You engineers get paid by the hour. We build. Anchoring for building things, you got to be a contractor, in my opinion. Now, design build and P3 is blurring those lines. Engineers are more part of the team. It would be like if I had my own PEs on staff and did my own design. We occasionally do some of that. Sometimes we have PEs on staff, but we're not doing permanent structures, so there is a big difference. So if you're deciding what you want to be in life, understand these little fundamentals. And just to be blunt about it, when it comes to contracting, eat or be eaten. You got to be tough. You got to be willing to go out there and fight for what you want to do. And you got to keep in mind that you're pricing things. And like I believe John Glenn or one of the other famous Mercury astronauts said, he's sitting on top of this rocket that was built by the lowest bidder. You got to get a job. You got to be the low bidder. But you also got to build something that your client wants. It's good for the public, and that you can sleep at night when you're done, because most of them should last 50 to 100 years or longer. So with that, I will turn it back to Erin and see if you have any questions.
Thanks so much, Les. This is Heather from UCA, and I'd like to extend the opportunity for people to submit questions through the chat panel. We only have a few minutes left, so I'd like to go ahead and read off a couple of questions that we've already received. But for those of you who are going to be leaving us, I'd like to remind you that we will have this session recording available on the UCA Young Members website in the next few days, and I'll be sending out an email so you can access that at your convenience. So to continue on with the Q&A session, the first question comes from Nick. Nick would like to know, how did you know that it took twice as long to drill the secant pile shaft if you were never able to initially install the secant piles when drilling in the planned geotechnical conditions?
No, we were able to drill them in the planned geotechnical conditions. The rock was decomposed, is what we thought. When our driller started, he got stopped about 5 feet below invert, and he's supposed to go 15 feet below invert of the tunnel. The first pile stopped, and he said he couldn't drill it, just as he try again and try different cutting tools. And the rest of the piles, he got to grade to the 15 feet below, and then we were able to go inside and hammer the material out. So we always thought that we could sump in 15 feet into the decomposed rock, which would have been 10 feet according to bore log. In fact, it was 27 feet that we had to drill through. So it had a major impact, and there was some claim about that impact with the owner.
Great, thank you. The next question, when you are proposing cutting-edge technology, do you bid with this or proposing it later as value engineering?
I didn't hear the question. You cut out.
Sorry. The question is, when you are proposing cutting-edge technology, do you bid with this or proposing it later as value engineering?
Depends on the specification. If the specification allows multiple different types of means and methods, I don't really consider that value engineering. We don't bid value engineering into a job. We bid what the specification calls for. So so I'm not going to say I would use a microtunneling or if I bid a more expensive method like microtunneling, when it called or said you could use a conventional TBM, and I know you can't do that because my experience says that TBM will fail, then I just bid in what I have, and if you call that value engineering, then I'm changing the means and method. Never have I can speak of say, oh, don't use a more expensive, more difficult method for the same price. Value engineering for us comes fairly rarely, and what we prefer is can be used, and we'll propose the right one. We know better than most engineers what to do.
Great, thank you. So we're getting a couple more questions in. Les, do you have time to continue answering questions?
Sure.
Excellent. Okay, our next question is from Pamela. Pamela would like to know, if it were up to you, would you rather support the microtunnel opening with steel casing pipe or precast concrete segments, and why?
We don't use precast concrete segments. You can use precast concrete pipe because we're doing pipe jacking. We're not installing the liner as we go on the tail of the machine, which is, we call that, we're pushing the from the outside, from the jacking shaft inward. Steel casing pipe is lighter, it's thinner, it's stronger, it gives us more work room. It has a much lower coefficient of friction on the outside. Frankly, we probably do 70 to 80% of our work is with steel casing. Concrete pipe has its place, particularly if it can be the one pass, and line and grade issues can be dealt with. Slight deviations from the mining are acceptable. We do that kind of work. We did, I think, 10,000 feet of that work at 72-inch and 42-inch in Indianapolis through boulder-laden ground. It can work well, but no, we prefer steel casing if we're doing a two-pass tunnel.
Great, thank you. Randall would like to know, any curved microtunneling project experience in rock? No.
In fact, my standard joke is we give you a free curve one every now and then when we make a mistake. The fact is, not seen in rock microtunneling. We are evaluating those conditions now to see if it's possible, but we're not thinking that's the right way to go. Now, if it was shale, soft rock, yes. Claystone, you could do that. In hard crystalline rock, no. The eccentric loading on the main bearing of the machine would be excessive. The wear on the cutters would be excessive. It's just not something that I think, given the scale of the machines and what they're designed for, would be a wise thing to do.
Great, thank you. The next question is a two-part question. Allie would like to know, when drilling the secant piles, why wasn't the new geology addressed in the drilling of the tunnel? And the second part, what would have been the impact if these correct conditions were known beforehand?
Well, I didn't get all the first part, but I think that's the same question you kind of got before. The impact here, if we'd have known there were 12 feet of rock here, we wouldn't have proposed a subaqueous excavation, which with a clamshell goes relatively quickly. We would have known that with no blast, we'd be down there hole ramming, and we would have priced in that additional work and the risk associated with going down without excavating. In limestone, you often get solution channels, which means if we hit a solution channel directly connected to the river, as we dug down, the shaft would have flooded. We'd have had to stop and grout it off before we could go back down and hole ram the shaft down. In fact, we were actually quite lucky. We did get water seeping in and then start to boil in under that one secant pile that was short, drilled. And thank God we forced the subcontractor to drill them all to grade and then fight for a change order to compensate him later on, because if he had not drilled these the full 15 feet down, I'm positive we would have had a heck of a time digging that shaft, because the bottom would have blown in right through the rock. It wouldn't have blown in the sense of that, but the water would have infiltrated so fast we couldn't have controlled it. Yeah, if we'd have known that this is where the rock was, we would have priced it differently and accordingly, but we didn't.
Great, thank you. That seems to be the end of our questions now. We have a lot of attendees that are starting to drop off the webinar session. So we'll go ahead and wrap up today. Les, would you like to give any closing statements?
I just welcome anybody to consider doing the contracting side. It's an exciting field. It's you have to be a little bit of a gambler. You have to be willing to take on a certain risk that is not part of what you think you go through, I think, in the education process of being a civil engineer or a mining engineer. But it's exciting, and it's you get the rewarding of being able to see the actual projects built, and to solve only come from actually doing the work instead of just thinking about it. And then within the industry, there's a lot of different types of profession within contracting. You know, there's actually being in the field, managing the people, managing the work, dealing with the problems there. There's in the office where you're doing the engineering, the estimating, the design work, temporary design works, or even sometimes permanent design works necessary to make something happen, and interfacing with your. And here I try to teach people that it all gets down to the 3 B's. You know, you have to bid it, you have to build it, and you have to bank it, and that takes a lot of different skills. So you can spend a lifetime trying to learn all those aspects. So it never gets boring.
That's great. Thank you so much again for presenting today, Les. This has been so informative. We'd like to invite everybody to reach out to Les with the information on the screen. Again, we'll also be sending out that email once the recording is available on the UCA Young Members website. And we'd hope you join us for the June 29th presentation. Everybody, we hope you have a great day, and thanks again for joining us.